All right, Kara, glad to see you're here. I was just checking to make sure I had done my posting right, but I'm glad you're here. Uh, haven't seen or heard from anyone else yet. Yep, it's just the two of us so far. Any questions, concerns, issues? Okay. All right, well, I guess the two Y chromosomes will be showing up sometime or another, at least one of them, hopefully. But um, before we get started today, I'm all set up to be started. I was going to go on and get started, if everything, just because it was past time. But let me go over just a couple of things that have happened since we last met. It's been quite a week, okay. And some of this, and you've heard this before because I think you were in another class. So maybe wait, both the other guys were in the class too. So I won't go into that in great detail, but just let you know this. Because of my health situation, we may be losing a Thursday class coming up sometime. I don't know if we will, and I don't know when it'll be. But there's a good chance I'm going to need another treatment. If it's the same treatment I've been taking, because it's been more than 9 months since I had the last one, they're wanting to do a two-stage treatment of it. So they're going to do a Thursday 10%, Friday 90%. Okay? Now, it depends on when they schedule me. But with this class being right in the middle of the day, there's an odds are whenever they schedule me, it's probably going to wipe y'all out. Okay? Maybe not, but there's a good chance it will be. Only if they schedule me late in the afternoon, which I don't think they will, is it likely that it will miss this class. So, I just don't know either if or when. Okay? And the reason of the uncertainty there is that the doctor wanted to do more blood work to, number one, make sure that the treatment he was planning to give me that I've had in the past, that has always been pretty effective, though it does sort of knock down my red blood cell count and my platelets pretty badly, and they're already very, very low. I'm quite anemic right now, and that sometimes when I just am running out of energy, of course it's right around noon, and I haven't eaten, and that's part of it, but the other part of it is I'm really anemic. Okay, so that's part of the issue here. But because of that, he's wanting to make sure that this is the best treatment, and he's also checking on the anemia and making sure there's nothing that either the treatment or the disease is causing the anemia, and that may change his approach to things too. So I won't know for sure until probably tomorrow. Went down and they did the blood work yesterday morning early. They may know by late afternoon today, but more likely sometime tomorrow. So I think there's a good chance that next Thursday and Friday I'll be taking a treatment. Okay? Now, it's a good chance if it is Thursday, it'll affect this class. I should know by Tuesday. So just hang on there, and we'll hopefully know by Tuesday. On top of everything else with that, a very good friend of mine has collapsed after a meeting at church on Tuesday night, and she is in ICU in critical condition, or at least the last I heard. Her social worker called me sometime this morning when I was in class or in between classes. I didn't hear it when she called. I need to call her back when I can get a chance to, and that won't be until after this class is over with. So the whole reason to tell you that, it could come up that I'm going to have to deal with some issues, because you see, I'm her contact person here. She has no family in the state of Alabama that she knew of, and she had a sister in Virginia, but her sister was quite a bit older than her, and she was 76. So the sister may or may not still be living, and if she is living, she may not be functioning too well, or and certainly so. I'm the contact person here in Birmingham, and so I may be called on to have to deal with some issues. So that's another distraction. I think maybe I told you all this at a previous class, but just to let you know, not anything is too certain right now, either with my treatment, my health, or with that situation as well. And on top of that, I'm anemic, so I run out of energy really quickly. Okay, all that said, any questions, issues, concerns of yours before we get starting today? Okay. Now, James, just a real quickie here. You just came in, you didn't hear all that. There is a pretty good chance that some Thursday coming up soon, could be as early as next Thursday, but may not be. I'm probably going to have a treatment for my CLL, chronic lymphocytic leukemia, and the odds are pretty good that it's going to affect this class. So normally I have my treatments on Fridays, but because it's been so long since I had the last treatment, they want to do it in 2 days, 10% the first day to make sure I'm still tolerating it fine, and then 90% the next day on Friday. So with this class being right in the middle of the day, well, here comes Miguel or Jesus, and so I'll say this all over again as soon as he gets in. Perfect attendance today, by the way. Way to go, team. Okay. Now, Jesus, I was just saying or explaining to the others, there's a really good chance that coming up some Thursday, we may have to miss class. The reason is there's a really good chance that I'm going to need to take I'm definitely going to need to take a treatment for my CLL sometime pretty soon, because the white counts are really, really high. They got to knock those back. But the bad news is that's bad news enough. The red cells, my hemoglobin, my hematocrits, and my platelets are all very, very low right now before the treatment, and usually the treatment knocks them back even further. So the doctor wanted to do additional blood work, which I went in yesterday to have that done, and the results aren't back yet. They said it would be about 48 hours because they're doing flow cytometry and some other stuff that takes a while, and they want to make sure that the treatment that I've been on, which has been very effective because it's been almost 9 months since my last treatment, but it also knocks down my white red cells, hemoglobin, hematocrits, and platelets, and he doesn't want to knock them back if that's not the best treatment, because they're already very, very low. So anyway, there's a real good chance that some Thursday, Friday, I'm going to need a 10% treatment on Thursday and a 90% treatment on Friday. But that 10% treatment, if it's in the morning, I probably won't be back for this class. If it's in the afternoon, I'll probably have to leave either before this class begins or sometime during this class. So there's a real good chance that some upcoming Thursday we will be missing this class. Don't know that yet. I should know hopefully tomorrow. Okay. And he wants to do it soon, so it could be as early as next Thursday if they can schedule me in the infusion lab during that time. If not, it'll be some other Thursday, Friday combination. So just to let you know that's going on. And then in addition to that, I'm the contact person for a good friend who is now in ICU at UAB Hospital. Basic last I heard was on life support, not expected to come out of it, and she has no family in the state of Birmingham, and I'm basically going to be the decision maker on issues. So that's coming up too. Hopefully it won't interfere with class, but there's no guarantee that it won't. So when it rains, it pours, doesn't it? Okay. Any questions from any of y'all before we get going today? Okay. We're in Chapter 2, Matrices, Section 2.4, Elementary Matrices, We're on page 78, near the bottom of the page, getting ready to talk about theorem 2.15. Now, I would type this, but it has enough subscripts and bolds and other things like this that maybe this one would be better for me just to write. So let's go for it. Starting off, I'm going to abbreviate some. If you got your books, you can read it there. But A is an n by n matrix. Okay? Now, square matrix, that's what the main thing here. We don't talk about the type of stuff we're going to talk about now unless it's a square matrix. Okay? Now, if A is an n by n matrix, here are 5 statements. We've seen 4 of them before. We're going to see more later. These are all equivalent statements. And here's the first of these statements. That A matrix there, that square n by n matrix here, that matrix A is invertible. We talked about that earlier. Okay? Now, if that statement's true, then this statement is true. If you have A multiplied by a variable vector equal to some constant vector, B, that equation has the pen's not writing, maybe I should have typed it, has a unique solution. If I do cursive, it does better, but it's harder to read. Has a unique solution for every n by 1 column matrix B. For every n by 1 column matrix B. I'm leaving out some words here. So, the other way to look at this, if this is true, that means A is invertible. If it has a unique solution, it's invertible. If A is invertible, this has a unique solution. Number 3. This follows from this one. If you have A, that same A invertible square matrix there, A, times X is equal to, now here they messed up some, okay? They wrote it as if it's a big 0. That should be the 0 vector, okay? And that has only the trivial, I better get the writing again. For some reason it does better in cursive. I'm not picking up the pen. Solution. Well, it has a unique solution. We know for this to be true, x equals 0 is a trivial a solution, but if it has a unique solution, that's the only solution, so that it only has the trivial solution. There are no others. And if that's true, the others are true. Number 4. This was the last one we did, I think. A is row equivalent to the identity matrix of that size I sub n. Okay? Now, that was, remember, how we determined that it has an inverse. We did augmented A with the identity matrix and then did row reduction. So A is row equivalent to the identity matrix. What you wound up with is the identity matrix where A was and its inverse where the identity matrix was. So if that's true, all these others are true. If any one of those is true, that's true. Okay? And here's the 5th, the newest one. Okay? A can be written as, sorry, my cursive writing is really bad, especially on this tablet. The product of elementary matrices. It's pretty bad writing. Okay. All of those are equivalent expressions. If any one of them true, the other four are true as well. Any one of them. Okay. Now, new subject here. We've done we factored basically a invertible matrix A, square invertible matrix A, factored it into elementary matrices. That's one factorization of it. There is another. This is just two matrices, and this is an LU factorization. Okay. Now, you might say, why do they call it LU? Well, that's what we're going to get to now. All right, for me to clear these? Okay. All right. At the heart of the most efficient and modern algorithms for solving linear equations, and that linear equation would be of this form: AX equal B. Now, if that represents the system of linear equations. If that system of linear equations does have a unique solution, remember, that means it's an invertible matrix. A is invertible. Okay? And if it does have a unique solution, we can also factor that matrix A into an LU factorization. They capitalize L and U factorization. So hard to write cursively with this ionizing pen, and really hard to get I's to dot. Okay, and T's to cross. In which the square matrix A, remember it has to be square for it to be invertible, is expressed as a product. A is equal to a product of some matrix L times some matrix U. Well, they still haven't told you what the L and U stand for yet. Now they do. L is what we call a lower triangular matrix. Okay, somewhere in there is an I. U, on the other hand, is an upper triangular matrix. Okay, that's what the L and U stand for. Now, what do we mean by that? Okay, a lower triangular matrix will be this: A11, A12, A13, dot, 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 but the last entry there is going to be, no, I'm sorry, I've said it backwards. I'm doing the upper. Oh, I can't remember which module I'm in. Lower triangular matrix, sorry about that. This has a 0 here, a 0 here, a dot, 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 and a 0 there. Okay, then it'll have a 2-1, a 2-2 with a dot 0 here, a dot, 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 and a 0 there. All the zeros there. I'm going to extend this down. A 3-1, a 3-2, a 3-3, then it picks up the zeros and a dot, dot, dot down to the last 0, and it keeps going like that until you get down to, remember, it's an n by n matrix, so a n1, a N2, a N3, dot, 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 all the way over to a N, N. Now, that's a lower triangular matrix. Now, I did a far bigger one than the one in the book. They just showed a 3 by 3, and perhaps I should have done that, so I should have been paying attention. Let me do just a 3 by 3, and that way I don't have the dot, dot, dots in it. A1100, A21, A220, and A31, A32, A33. That is a 3 by 3 lower triangular matrix. What it means is use the main diagonal as a line. That makes a triangle. Everything inside the lower triangle, the triangle below the diagonal, you have potential values. Everything above the diagonal, every one of them has to be a 0. The diagonal generally will not have any zeros in it. If there was a 0 in the diagonal, you don't have an invertible matrix. So all these will be entries that are non-zero. These down here, some of them could be 0, that's okay. But everything above it is a 0. Now the upper triangular matrix would just be the reverse of that. A11, A12, A13, this is just a 3 by 3, 0, A22, A23, 0, 0, A33. So do your main diagonal. That can contain no zeros to be an invertible matrix. No zeros there. There'll all be numbers there. And these may or may not be zeros up here, but some of them will be numbers. But everything below that main diagonal is a 0. So this is upper triangular, lower triangular. That's what we mean by upper and lower triangular matrix. These two are 3 by 3. You can have 4 by 4, 8 by 8, 9 by 9, 15 by 15. Okay. So, with that in mind, let's see if I can get this definition down. Do I have room? I think maybe so. Let me try it. If, maybe not, okay, the n by n matrix A, I'm going to abbreviate, matrix A, can be written, oh, I have a phone call coming in. Let me see what it is. Oh my friend just died. So I need to call, but I'm going to wait till after class because that will turn into a long phone call. So anyway, sorry. We knew it was coming, but it's still a shot. Okay. Okay. Then A can be written. I hope I can carry on here. As the product of a lower triangular matrix L and an upper triangular matrix U, then A is equal to LU. That is the LU factorization of A. Okay. Now, of course, A has to be square, and by the way, it does have to be invertible. Okay. They didn't mention that here, but it is. But if that M by M matrix A can be written as a product of the lower triangular matrix and an upper triangular matrix, L and U, then A is equal to LU is an L factorization of A. Okay. All right. Okay, this is tough. How are we doing? We go to 11:45. I mean 12. I can't even think anymore. 12:45. So let's see if I can hang in there. Okay. Here is a 2x2 matrix. 1, 2, 1, 0. Now, that is not an L or an U matrix. There's the main diagonal. You don't have zeros above or below. Okay. It is, however, now maybe I said it wrong. Yeah, I said that the diagonals can't be zero. They can have zero in them. It's only when you do the LU factorization that can't have zero. The original matrix can have zeros on the diagonal, but when you do the LU factorization, neither the L nor the U can have a zero in there. Okay, that's what I meant to imply. I don't think I said it that well though. Okay, now what they're going to do, they're just going to tell us what it is. They aren't going to tell us how they got it, but they say that this matrix here, 1, 0, 1, 1, that is a lower triangular matrix. That's an L. This is your A, okay? Because the only thing above the main diagonal is a 0, okay? Times U, which is a 1, 2, 0, negative 2. There's your main diagonal. No zeros in it. Numbers above it, but not a number, but a 0 below it. Only 0. That's an upper triangular matrix. Okay? So this will be your LU factorization. Now, let's verify and make sure that is indeed right. Right. First row, first column, that'd be 1. Yep, we got a 1. First row, second column here, that would be a 2. Yep, we got a 2. Second row, first column, 1. Yep, we got a 1. Second row, second column, 2 minus 2 equals 0. Yes, those do multiply. This is a lower lower triangular matrix. This is an upper triangular matrix. This forms your LU factorization. Okay. Now, let's do one a little bigger. Now again, we're not seeing how they did it, but they're just showing us they can do it. Here's our A 3 by 3, has to be square by the way. 1, negative 3, 0, 0, 1, 3, and 2, negative 10, 2. All right. Now they claim that this can be written as a product of 1, 0, 0, starting off to be lower triangular, 0, 1, 0, still lower triangular, okay, 2, minus 4, 1. Yep, that's lower triangular. Main diagonal is not got a 0 in it, and you got zeros above it, You can have them below it, that's fine, but not all of them are 0. Okay? Times 1, -3, 0, that's okay. 0, 1, 3, that would be necessary to have that 0 there. And 0, 0, 14, that certainly 14, that qualifies as a upper triangular matrix. That's a U. Now let's check and make sure they're not pulling the wool over our eyes. Let's do our multiplication. First row, first column, that's just going to be a 1. First row, second column, that's going to be a -3. First row, third column, that's going to be a 0. Second row, first column, that's going to be 0 plus 0, 0, that's a 0. Second row, second column, that's going to be a 1. Got it? Second row, third column, that's going to be a 3. Got it. Third row, first column, that's a 2. Third row, second column, that's a -6 minus 4 is -10. Yes, that works. Third row, third column, that's a -12 plus 14, that's a 2. Yes, that works. That is your LU factorization of that matrix. Now, there is a little blurb at the bottom of the page 79 there. It says computational fluid dynamics, that's called CFD, is a computer-based simulation of such real-life phenomena as fluid flow, heat transfer, chemical reactions, those kinds of things. Guess what? They use linear algebra to solve their systems of equations in the computational fluid dynamic. I'll let you read that. They say aerospace companies like Boeing and Airbus used CFD analysis in aircraft design. Okay, I wish Boeing would have used it on their Dreamliner. Okay, that was a snide remark. All right, so they've shown us some, they haven't shown us how to get them. Okay, here is what we do. Gonna clear the screen. Any questions so far before we move on? Okay, here's our matrix A. Okay, 1, -3, 0. 0, 1, 3. 2, -10, 2. Okay. Now, how do we find that factorization? Well, here's what we do first. Start your row reduction process, and you know in the row reduction process you're going to get, and this is Gaussian elimination, you'll get 1 with zeros below it, 1 with a 0 below it. Hey, that's going to form an upper triangular matrix. So doing that is going to head you in that direction. Okay. Now, but as you go, keep up with what your elementary matrices were that are going to produce that. So again, I'm going to write over here your I sub 3, because that's a 3 by 3. We'll write this one, a 1, 0, 0, 0, 1, 0, 0, 0, 1. All right. So let's do our row reduction. This would become, we want and have a 1 in the upper left. That's fantastic. That's exactly what we want. Okay, going to do row reduction here. We got a 0 there. That's what we want. So the first row stays the same, 1, -3, 0. Second row stays the same, 0, 1, 3. They've made it easy for us. all we have to do, well, for right now, is do minus 2 times row 1 and add it to row 3. Okay? So that becomes a 0. Minus 2 times 1 is minus 2 plus 2 is 0. Minus 2 times minus 3 is plus 6. Minus 10 is minus 4. Minus 2 times 0 is 0, plus 2 is 2. Okay. Now, oh man. We need to do the same thing here to get our E1. Okay. Same operation here. Negative 2 times row 1 added to row 3. So row 1 we leave alone, 1, 0, 0. Row 2 we leave alone, 0, 1, 0. Row 3 becomes minus 2 times 1 is minus 2 plus 0 is minus 2. Minus 2 times 0 is 0 plus 0 is 0. And minus 2 times 0 is 0 plus 1 is 1. So there's your first elementary matrix, E1. Okay. Now, next thing we want to do, remember all we're doing is Gauss elimination. We want a 0 here, so this will be 4 times row 2 plus row 3. Okay, so this will become leaving row 1 alone, 1, negative 3, 0. Leaving row 2 alone, 0, 1, 3. We'll operate on row 3 here. 4 times row 2, 0 plus 0 is 0. Fantastic. 4 times 1 is 4 plus minus 4, that's 0. Fantastic. 4 times 3 is 12 plus 2 is 14. All right, now that gives us an upper triangular matrix. But over here, we need to keep up with our E2 here. Now remember, we don't go back to E1, we go to the I at the top. And we're doing 4 times row 2 plus row 3. So top row 1 stays the same, 1, 0, 0. Row 2 stays the same, 0, 1, 0. And row 3 becomes 4 times row 2, so that would be a 0, 4, 1. Okay, I hope you followed that. Okay, that's what they got in the book, which is heartening. Now, this reduced matrix here, that is an upper triangular matrix U. Okay? Now, we know that from what we did before, in fact we just did it, that if we started with A and multiply it by E1, you would have gotten this, and multiplied that by E2 on the left, you would have gotten that. Okay? That gave you U. Now, what we're going to do, and I kind of blew that a little bit. I knew I was doing it when I did it, but I didn't stop myself in time. Let me put the U over here. Okay. What we're going to do now is multiply this thing on the left by E2 inverse. And I'll multiply this by E2 inverse. Now that will make this become the identity matrix, I. Then we'll multiply by E1 inverse, and that will multiply this by E1 inverse, and that's going to make this become the identity matrix. And then you're left with A times the product of these two things. Well, that's better be L. Then you've got the L2 factorization. So what we didn't do and should have done was identify what E1 inverse was, and that was, okay, 1, 0, 0, 0, 1, 0. It's the operation you do to make this become a 0. Let's multiply 2 by row 1 and add here, so that would be a 2, 0, 1. Your E2 inverse here would be what you would need to do to make this go back to an identity matrix. That would be to multiply the second row by -4 and add it to the bottom. Do that to the identity matrix and you get a 1, 0, 0, 0, 1, 1, 0, and 0, -4, 1. That's an ugly 4, isn't it? Okay, now we got to multiply those together in that order, E1 times E2 inverses, right? So that's going to form a 3 by 3, multiplying this one by that one, just like you see here, what you see here. Okay, so it'll be first row, first column, that's going to be a 1. First row here, second column here, that would be a 0, plus 0, plus 0, that's going to be a 0. Good so far. First row times third column, 0, 0, 0, 0, 0. So far, so good. Second row, first column, that would be a 0, 0, 0. So that's a 0, which we weren't sort of expecting. Second row, second column, I can see that's going to be a 1 because the only thing in either one of them. Well, wait, yeah, no, that's right. It's a 1. Second row, second column, yeah. And then second row, third column is going to be a 0, 0, 0. So far, it looks like a lower triangular. Let's see what the next one is. First row, third column, that's a 1. No, I'm sorry. I said it backward. Third row, first column, that's a 2, 0, 0. So that's a 2. This is a third row, second column, 0, 0, -4. I think that is, yeah, -4. And then the third row, third column is a 1. So that is a lower triangular matrix. Is that the factorization? Can we multiply L times U? Now, I don't have a lot of room left. So what I'm going to do is erase some stuff here. If I go to the right eraser. Now let's erase this. Okay. And let's see if we can multiply those two together. I keep going to the wrong place. My mind isn't here today, folks. Sorry about this. 1, 0, 0, 0, 1, 0, 2, -4, 1. That's the lower triangular matrix. Multiplied by this one. 1, -3, 0, 0, 1, 3, and 0, 0, 14. And by the way, why don't you just look across the, no, I'm sorry. Nah. Yeah. flip back one page to page 79. Look at the B problem. Okay, we have 1 0 0 0 1 0 2 4 2 negative 4 1 times 1 negative 3 0 0 1 3 0 0 14, and that's the right hand side of your B part. Your left hand side of the B part was this matrix here: 1 negative 3 0 0 1 3 2 negative 10 2. So we don't have to multiply them. We've already done that. We did it on the last problem. They do form matrix A. You can do it again if you'd like, but why take the time to do it? Sorry, I'm running out of steam really fast. All right. I'm not sure that'll help much. Best I can do at the moment. Okay. So let's sort of do a summary here. This is sort of the bottom half of page 80. If your matrix A, which we start with up there, row reduces the upper triangular matrix U, which we did. There's matrix A. Let's just do a quick recap. Row reduce that to an upper triangular matrix U. Okay. Using only the row operations of adding a multiple of one row to another row below it. Okay, now that's that's the key here. If that only uses that one elementary row operation, only multiplying a multiple of one row added to another row to get it in row echelon form, not reduced row echelon form, row echelon form, that forms an upper triangular matrix. Okay, now keep up with the elementary matrices that do the same thing, and they're all very similar to what we just did. They're all multiplying one row to a multiple of one row to the identity matrix and adding it to another row. Okay, now the multipliers we used here was a -2, if I can get my pen to show up, a -2 here and a +4 there. They show up over here as a 2 and a 4. A -2 and a 4 here, and when you do the inverse matrices, a 2 and a -4 there. Okay, I couldn't read my writing, but okay. Those are your opposites of the entries here that you see here, 2 and -4, that you have in the lower triangular matrix. Okay. Trying to follow what their logic is here. That is true in general. If U can be obtained from A using only the elementary row operations, adding a multiple of one row to another row below it, then the matrix L, lower triangle matrix, is ones along the diagonal. Now that we happen to come up with. That's not always going to be the case, but it was the case here. Notice we didn't start with that. We didn't have ones along the diagonal here, and we didn't have ones along the diagonal there. Okay. But in the lower triangular, we did wind up with that. then the negative of each multiplier is in the same position as in the corresponding 0 in the U of the main diagonal. Boy, they sure make that difficult to read. Okay. Once you have obtained the LU factorization, you can then solve a system of n linear equations in n variables. Remember our good old ax equal b. Solve that equation where this is the a that we had here. Has to be square, has to be, so far we've talked about invertible. They haven't said that yet, but it is. Then you can use a system of n equations, n variables to do that. And it says very efficiently in 2 steps. Now these 2 steps are not, in my mind, particularly easy to follow their reading, but when you're actually doing them, they're not that bad. Okay? So, this is not the class I would have liked to have done on a day like today, because this is a little complicated and my mind's not right with me here. So let me clear the drawings here. Okay. Once you've obtained the LU factorization of matrix A, then here's what we do. First, write y, now we don't even have a y anywhere seen here, is equal to u times x. Now x was the variable matrix there. Whatever that produces, that becomes your y. Okay? And they say this is 1 step, it's really 2. Solve Ly, that's the lower triangular matrix. I say y and wrote a u. Ly is equal to b. And that, by the way, that's a vector, for that y. Now, I'll sit and look at this and say, what in the world are they talking about? Okay. Here they say write this, and that gives you a y. Here they say L times that y, which we got from here, equal b, solve for y. Okay. Well, you just solve for y. Okay. So it seems a little circular here, but hang on with it. Okay. I don't think their instructions are all that clear here. Number 2, which is, to me is number 3, solve ux, that's the upper triangular, times x, which we already know to be y, is equal to y. But solve this for x. Okay? Now, it seems a little crazy here, but that's what they have you do. Now, this column matrix X here is your solution of the original system of equations. Remember that was AX is equal to B. That was your original system of equation. But that AX was also equal to LUX equal B. Okay? But the LUX, because UX here is Y, that was L times Y equal B. Okay? Now, they say the second step. Sort of hard to determine when they talk about second step. This one up here, this one down here. I think they mean this one. And this is where all their letters really don't make anything all that clear. Probably is absolutely correct, but it's far easier to, well, it's easier to see when you're actually doing it. Okay? It's back substitution because the matrix U is upper triangular. Okay? And the first step is similar, except it starts at the top of the matrix. This one I think it is, it's lower triangular, so the first step is often called forward substitution, and this is called back substitution. Okay, now a lot of blah 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 there. Okay, let's clear the screen and try to do example 7. Now, the good news about example 7, you can go to larsonlinearalgebra.com and see an interactive version of this type of example. So we're going to start with a system of linear equations. X sub 1 minus 3x sub 2 is equal to minus 5. X sub 2 plus 3x sub 3 is equal to negative 1. 2 x sub 1 minus 10 x sub 2 plus 2 x sub 3 is equal to minus 20. Now, if you haven't noticed it yet, okay, this matrix of your coefficients here, 1, negative 3, 0, 0, 1, 3, 2, negative 10, 2, is exactly what we had in example 6 across the page. So we've already done that. We've done this. Our matrix A here is 1, negative 3, 0, 0, 1, 3, 2, negative 10, 2. Exactly what we had before, and we've already done this, so there's no reason to redo it. I think we could have stood the exercise of redoing it if they had given us a different system of equations, but they didn't. So this is 1, 0, 0. This is the lower triangular matrix, 0, 1, 0 from the previous page, 2, negative 4, 1. That was your lower triangular matrix times the upper triangular matrix, which is your 1, negative 3, 0, 0, 1, 3, 0, 0, 14. Go back, look at your notes, and you'll see that's what we got for your LU factorization of that. Okay. Now, what we're going to do here they say let y equal ux. Okay? Now they just say that. Y is equal to ux. They don't write it down. They just say let that be that. That's all you do. Don't write your upper triangular matrix and do it times x and do that. Just keep that in mind. That's what your y is. This is the part that's sort of squirrely. Okay? Now, they then say solve this equation, Ly, here's your L, is equal to B. Okay, we have the L here. That is 1, 0, 0, 0, 1, 0, 2, negative 4, 1, times y, and we don't know what y is. We know we're going to come back and call it this in a minute. don't worry about it. Okay, we'll just call it y1, y2, y3. Okay, and that's equal to your b. Your b here was -5. It's supposed to be a 5, -1, -20. Okay, it says solve that for y. Okay, that's your y. Okay, now that would be looking at this times this. First row, first column, that'll give you first entry here. So this is obviously y1 is equal to -5. Okay, then this times this will give you y2 is equal to -1. And then this times that would be 2 times y1, which would be a -10. This is why they call it forward substitution. -4 times a -1, that's going to be +4. Okay. Plus y3, we don't know that one yet, so that would be y3 is equal to -20. Okay. Now, this adds to be -6. So y3 must be -14, because you add 6 to both sides and you get -14, y3. Okay. Now, that gives you your y. We just solved for y. So your y is equal to -5, -1, -14. Now, don't think they're all going to be quite that easy, because you never change this because these things were so simple. Okay, most of the time that's not going to be a 0 there. That's always going to be a 0 there. I mean, zeros here. So that first one's always going to be easy. The next one won't be quite as easy as this one, because you'll have to do forward substitution in that as well. So there's your y. Now, that's what we just solved here. Now we do U, the upper triangular matrix, which is 1, -3, 0, 0, 1, 3, 0, 0, 14 times your x, okay, and that's equal to this y we just determined, -5, -1, -14. Now the way to go on this is from the bottom up, back substitution. This times this will give you this one. So I think you can look at that and say x sub 3 has to equal -1. Okay, back up to this one. X sub 2, we don't know. 0x1 plus 1x2 plus 3x3, which would be x sub 2 minus, goodness gracious, 3 is plus 3 times x sub 3, where x sub 3 is -1. That's equal to -1. So this tells you x sub 2 is equal to 2. Add 3 to both sides. Then plugging both of those in, this top one gives you x sub 1 minus 3 times x sub 2, that would be -6, is equal to minus 5. So 5, and that gives you x sub 1 is equal to 1. So there is your solution vector. 1, minus 1, minus 1. Let's see if that's what they got here. No, I did something wrong. It's that middle one. I don't know. My brain's not working. Let me make sure I did it right. Yeah. Okay, let's start again. This will give you x sub 3 equal minus 1. This gives you x sub 2 minus 3 is equal to minus 1. X sub 2 minus 3 is equal to minus 1. So x sub 3. Okay. I have completely lost where I'm going here. So x sub 2 was 2, and I wrote down minus 1. I wrote x sub, sorry, I had it right. I just wrote it wrong. Goodness gracious. Like I said, my brain's not here today. Okay. X sub 1 was 1. X sub 2, right here it is 2. I don't know where I think I went over to y sub 2. Okay, that's where I did. And x sub 3 is minus 1. So yeah, we got the same thing they did. First is back substitution followed by forward substitution. And folks, that does finish 2.4. Okay, homework exercises here would be any of the odds 1 through 7. They're all at Calc Chat. Either 9 or 11, they're both at Calc Chat. Any of the odds 13 to 17, they're all at Calc Chat. Any of the odds 19 to 23, they're all at Calc Chat. Either 25 or 27, both at Calc Chat. Either any of the odds 29 to 35, they're all at Calc Chat. You can do 37 if you'd like. It should be at Calc Chat. 39 should be at Calc Chat. 41 should be at Calc Chat. Either 43 or 45 should both be at Calc Chat. 47 should be at Calc Chat. 49 to 51 should be at, or 51 should be at Calc Chat. 53 should be at Calc Chat, and then you can do any of the odds 55 through 61. They should all be at Calc Chat. All right, now that finishes 2.4. Now, if you flip the page to 2.5, they're talking about Markov or Markov, I don't know which way you pronounce it, chains. These are called stochastic matrices and Markov chains. Okay, these are dealt a lot with in probability. They give some examples here. You can look at them. These take a while to do, and there's nothing in the course description that I recall that said anything about Markov chains. So I'm willing to skip this. But before you do, you might think, who is Markov? That could be a good paper topic. Or, how did he develop this? That might be a good one, might be sort of tough. Or, who uses this? Okay, that would be a very enlightening thing. It could be your major uses this. I kind of doubt it, but it could be. Okay, so I say don't skip this. Look over it, see if there's anything here that you would like to use as a Markov chains, as a paper topic. Sorry, I can't talk. There's a linear algebra applied. Google's PageRank algorithm uses Markov chains. Okay, Now, I don't know if you recall, but Google made its mark on the computing world by coming up with a search engine that just beat everybody else's in the ground. I wouldn't be at all surprised if they didn't use Markov chains. So there may be a very practical application. Will you be able to find out how they did it? No way in the world. That is a very well kept trade secret. So don't try, but you can work around the edges of it. So that section is dealing basically with Markov chains, talking about all sorts of things: steady state, absorbing, regular stochastic. There's just so many things here in this section, it would take us a while to get through. And the course description didn't call for it. So I'm all in favor of skipping this, but I suggest you take a look at it. Look at some of the applications they give. Spread of a virus, number 12, that wouldn't be one that's answered in the back of the book. That's exactly what we're dealing with today. You'll see other things, sports activities, smokers, non-smokers, all sorts of things there. Fundraising. If any of this is something that you think you'll be running into in your field of study, you may want to take a look at it. I kind of doubt if most of you will. So let's move on to 2.6. 2.6, more applications of matrix operations. Markov chains was one application. That's what this chapter is all about. Okay. 2.6 gives you some more. First of these, cryptography. Okay. And basically this opens up all sorts of potential paper topics. There was a, what do they call it? Encoding. Cryptographic thing that helped us win World War II. Okay, so there's some history involved here. If my memory's right, it was called the Enigma Code, and I believe it was the British that broke the German Enigma Code, but they couldn't let them know they had broken the code, because if they did, they'd have come up with a new code. If you did see the movie that was on Churchill a few years ago, I can't think the name of it, I'm almost certain that came into play. They broke the code, or they intercepted a message by using the broken code, and found out one of their forts, establishments, was going to be attacked. But if they had defended it, the Germans would have known they broke the code. So poor old Churchill had to let those people die just to keep that code, the fact that they had broken the code, a secret. And one of the people that worked for him in the movie, well, this may have been Hollywood, actually had a brother that was in that unit. So she had to type out the orders or whatever she had to do that basically sealed his death. So it was, warfare is terrible. Okay, there's a linear algebra applied there. You can look at that one. If you're into cryptography, this may be something you might want to look at. Then over on page 97, there's a thing called Leontief input-output models. And it seems like you run into these in so many texts, and so far, and it's talking about an American economist, Wassily W. Leontief. I don't think his family was from the U.S., but he published a model concerning input and output of an economic system, received a Nobel Prize for his work in economics, and this is talking about this. And every time I've done it, I find out, I think to myself, what's the point of all this? But there is a point. Economists use it. I'm not an economist. My older brother is. He'd probably eat it up. I find absolutely, but you can write on who in the world Wassily W. Leontief is, how he developed this, who uses it, that type of thing. There's another application of matrix operations. Least squares regressions. This is a very big usage of linear algebra, and it's used all over the place. You may wind up in your field of study using it. You'll probably use some package that you don't have to do all the grunt work, but if you want to see what the grunt work's about, here it is. Okay, least squares regression. You'll find lots of things about that if you wanted to write your paper on that. It's also sometimes called linear regression. Okay, so there's another thing, and that ends 2.6. You don't have to do anything there, but that comes to the end of the chapter, and if you're interested in more homework, more practice problems, and these are also at calcchat.com, any of the odds 1 through 5 would be good. 7 or 9 would be good. They're all at CalcChat. 11 or 13 would be good. They would go over transposes of matrices. 15 or 17 would be good. Any of the odds 19 to 25 would be good. Solving a matrix equation, 27 would be good. 29 good. 31 good. Either 33 or 35, very good. Either 37 or 39. 41, 43 or 45, that was the LU factorization, which we did today, and 47 also uses that. After that, you get into these last ones that we did not do, so don't feel you have to go any further than that. All right, and there's quite a few of all these, so if you're interested in any of those, go for them. Okay, now that takes us, oh my goodness, we've just run over, haven't we? Sorry about that. I thought we had more time. Okay, can that be right? Yeah, we go to 12:45, that's right. Okay, sorry, we went 5 minutes over. There'll be no extra charge. Now my question to you, or my statement to you, since we did finish chapter 2, I will be posting hopefully sometime this afternoon, but if I don't get it done this afternoon because I've got to deal with this other thing, it'll be tomorrow, hopefully. I'll post your chapter 2 test. Okay, so be looking for that. Not right away, because I know I've got a phone call to make, and that's going to be a long phone call. I've got lunch to eat. I don't know if I even have time for that. I've got another class today that goes from 3:15 until 7:45. So I don't know if I'll get to post it today, but hopefully tomorrow. Okay, any questions? All right, sorry about running over. Sorry about being a little disjointed today. It's not been an easy time. So I'm going to stop the recording. Any last thoughts, parting shots before I end the meeting? Take care, folks. Have a safe weekend. Have a good weekend. But boy, be careful. I mean, the weather's beautiful. There's such a temptation to get out among friends. Be careful. You know it's going around. It's going around big, big time. Take care. See you next week. Bye-bye.